Okay, some 2 decades ago or so, when I didn't know Maha very well at that time, a common friend told me, Maha thinks faster than everybody else, and for which you have my pure jealousy, Maha. And he does this awe-inspiring science, like so much amazing stuff. And it's also a pleasure to know Amla and you. So happy birthday. Streaks in viscosity varying flow. So this talk is about streaks in viscosity varying flow. Streaks are everywhere in shear flow. Viscosity variation is everywhere, whether shearing or not. And so it is time to look at the two together because nobody looks at the two together. And this talk is based on these papers. Basically, this paper, it breaks down the linear part and provides a bit of insight. And this paper shows how nonlinearity is very, very different when you have viscosity stratification as opposed to when you do not. And the answer, the conclusion is that we provide a new mechanism for streak formation, streak generation. Then this new mechanism can compete or cooperate with the standard one, and the standard one gets changed also. And viscosity breaks symmetry fundamentally and modifies the route to turbulence. So these are the things we want to say at the end of this talk. So like when you increase Reynolds number in shear flows, we all know that at some Reynolds number, there's a departure from the steady laminar solution. So after that, the solution is not steady laminar. And you know, in the standard ones we are used to, like Square's theorem is obeyed and you get, you know, disturbance structures which are aligned in that way compared to the flow going this way. So that's basically a span-wise alignment of vortices. So that's what happens. But in many, many wall-bounded flows, the opposite happens. You get vortices which are stream-wise aligned. So you get vortices like this. And because you have vortices like this, why do you have vortices like this? Basically, like suppose you have vorticity in all directions and there is a mean shear in this direction, that omega in that component of the vorticity is bent around or turned around by the shear and it gets streamwise aligned. So basically, in other words, it's omega dot grad u in the vorticity equation in action. So this is what pushes it in that direction. So now what is a consequence of streamwise aligned vortices? The consequence is that like when two vortices are oppositely signed, they will pull fluid from here to there, they will pull fluid from there to here. So like in a shear flow, near the wall, the velocities are low. Away from the wall, the velocities are high. So you're going to get low speed streaks pulled up, high speed streaks pulled down. So you're going to get streaks because of these aligned vorticities. And this has been known and studied for a very long time. So streaks are very, very important. And so streaks are everywhere. This is the first thing. They are born, they move around, they die, whatever, but they are everywhere. We talked about the first departure from laminar state, right? But look at fully developed turbulence at very, very high Reynolds number. Simulations in a channel, simulations in a pipe, everywhere. And these colors are like fast and slow flows. So you see how they're all streamwise aligned in this phenomenally turbulent channel and pipe. Boundary layer, look at that, it's an experiment. Then there are many such experiments. Couette flow, Earth's atmosphere at a scale of 6 kilometers. There are these streaks. So basically, streaks are everywhere. Observation, simulation, experiment. Turbulence, therefore, is neither homogeneous nor isotropic. You want to understand real-world turbulence, you need to understand streaks first of all. And streaks are everywhere. Now, viscosity stratification is also everywhere. So this is a picture from our hopefully forthcoming paper. Now, we're going to talk about these large scales. In the mantle, Earth's core, you have like, 15 orders of magnitude variation of viscosity. It's not some small number. It's like very, very huge variation. And then there are pipe flows and atmospheric flows and things like this. These are our concern. Anywhere where you have a slight temperature change or a slight change in concentration of anything, you have viscosity variation. So standardly, nothing is of constant viscosity, although we pretend everything is at constant viscosity. that we get away with it a lot of the time, but we can't get away with it also a lot of the time. Okay. So why are we worrying about all this? Just because those two fields are mature fields and they've not come together, are we just blindly putting them together because nobody did that? No. Lifetimes of streaks are important in so many processes, and viscosity variation is going to deal a heavy blow to this, everything we know in this. Viscosity variation is a fundamental modification. It's a physics modification. It breaks symmetry. It does many things. It's not just some numbers that we are after. So this is why we study it. Now, in these shear flows that I told you, the wall-bounded ones, there is usually a subcritical transition to turbulence. So there's always a coexistence of attractors. So at the same Reynolds number, you have a laminar attractor and many other attractors like turbulent and other such attractors. And these attractors are separated by these basin boundaries shown in red. Now the point is that, let's say a channel or pipe flow, it's an infinite dimensional state space, right? So there is a U, V, and W at every X, Y, and Z. And in a laminar flow, I've shown that infinite dimensional thing as one point because we know the U, V, and W everywhere. So that's a point. In a turbulent flow, it's like a chaotic attractor. So typically, there is a big game in this field where we look for this thing called the minimal seed. In other words, we ask, what is the closest approach to the laminar where you're already sitting in the basin boundary of the turbulent attractor. So how tiny a perturbation do you need to do from the laminar, and in what special direction in this infinite dimensional state space to go there? And typically you will find that the minimal seed thing consists of streaks. So, yes. No, sorry. I meant that if your Reynolds number is very low, then like the turbulent attractor won't be there. The basin boundary will shift there. But as you increase the Reynolds number, the basin boundary shifts here. That's basically the model. Is that okay? The linear state is linearly stable. Yeah. This is a state where, so this is a subcritical transition where I have two or more attracting states. So each attracting state is linearly stable. It's linearly stable, but it can show transient growth, which makes it unstable. Okay, so the equations that we are going to talk about today. So what we are going to do first is a linear thing, where we take the we linearize the viscosity varying Navier-Stokes. We put Kx equal to 0. That means we are looking only for streaks. We're looking for these solutions. And this is all standard in the game now. So we then put perturbations, we Fourier transform them. We put a particular wave number in the span-wise direction. You saw that these streaks have this very nice way of, some equal spacing. So we put this as the span-wise wave number and a frequency. So this we put it back into the Navier-Stokes. We get this bunch of equations, namely these three equations where those operators, the Sommerfeld operator, square operator, and the temperature operator, they're all given here. Now, the black stuff is what everybody has been looking at when they study streaks. The red stuff is what is modified by viscosity stratification. So what used to be the velocity perturbation, mean velocity gradient is modified by the viscosity stratification. Viscosity itself is a function of space and so on. So these are terms which are modified compared to the old, and the blue ones are absolutely new terms which come due to viscosity variation. So what we've got here is we've got a flow where we prescribe a mean shear, and then we prescribe some temperature or other variation, and that variation provides a viscosity which is a function of space, and given all that, we plug it back into the Navier-Stokes and derive these equations. And these Navier-Stokes things are linearized. So what we've done is we've got these forcing terms which actually include all the nonlinearities in the Navier-Stokes.
There is a new length scale or set of length scales that you use with viscosity certification? Just one, or do you have a spectrum?
So you can do a bunch of things, and each of them provides a new answer. For example, like if you're looking at two fluids, let's say glycerol and water or something, which will diffuse very, very slowly into each other, you're introducing a very thin length scale, which is changing in time. So that is completely independent of the length scale of the flow. Whereas if you have a temperature variation across, then you're putting the same length scale into that as the velocity. And each of these, like the former one can actually lead to brand new instabilities, which is not the topic for today, but it can actually lead to some very interesting instabilities when this critical layer overlaps with that tiny layer. So things like that can happen. So these are the equations we're going to be dealing with. Now, with Anagha, who's a genius in this kind of thing, we looked at two flows, Poiseuille flow and Couette flow. And in these flows, we put a temperature variation, a linear temperature variation in the mean across. And then we studied those linearized equations. So here are the forcing terms. You're forcing this flow, and the forcing is going through these operators, and then it's coming out as Q hat, V hat, W hat, and so on. U hat we'll call as streaks, because these are the perturbation velocities which take you away from the mean velocity. So we saw those low speed streaks and high speed streaks. They are basically the magnitude of U hat, which is the streamwise velocity. I forgot to introduce the coordinate axis and all, but yeah, this is basically the thing.
The length scale associated with which streak is essentially chosen, the fastest growing?
Yes, we'll come to that. So basically, what spacing, that's what you're asking. Yes, we'll come to that. So now what we have is, we have Reynolds number multiplying some of these. And we're going to throw away that dashed line and this dashed line, because they have only one Reynolds number, whereas these guys are Reynolds square. So they're Reynolds relative to those. So we throw away those to make life easy. So then we have these two forcings, and we have two routes to formation of streaks. One route is just the traditional route, la, 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 and in that traditional route, this thing, this term is modified by the viscosity stratification, and some of these things also will have modification terms. The other route is brand new. The other route to streak formation is brand new. It comes entirely due to viscosity stratification. And now we do a singular value decomposition, simple analysis on this, where we say root 1 plus root 2, whatever root 1 plus root 2 does to force and produces streaks can be broken up like this, where the forcing is given by each of these singular functions. And then we maximize over all kinds of frequencies to get this thing called phi m, which is the best forcing you can do to get the best streak generation. And the resulting streak generation is given by this singular value multiplied by psi 1, the shape, the Z shape of this streak generation. So this is basically a standard method in order to get the best streak you can for a given forcing, like a unit forcing. So that's basically what we do. And in this, we're going to prescribe a length scale. We're going to prescribe the wavelength and do this, and we'll repeat it for all wavelengths. And then we'll ask who does best, which produces the biggest streak. So this is basically like, the amplitude of the streak for the amplitude of the forcing. And yeah, one thing which I forgot to tell in the previous thing is that, you can have pretty weak vortices, but they can produce strong streaks, because all you need is that it's lifted this velocity there. So this amplitude can be really big, and that's what we're looking for.
But this is still a linear analysis.
This is all a linear analysis. Okay, and this is the result we get. We did this linear analysis on the laminar mean as well as the turbulent mean flow. So in the turbulent mean flow, you can say that all those funny perturbations are very fast compared to the streak formation. Streak formation is the slowest. If you do that, then you're justified in using a turbulent mean and repeating this exercise. And remember that this may be a linear exercise, but all the nonlinear terms are clubbed into the forcing. So we're pretending that the nonlinears are forcing this flow. Now, this is the main result. What we've done here is that we've separated the less viscous half of the channel from the more viscous half of the channel. And then we've done that for Couette and Poiseuille, and these are the parameters we use. Now, R1 is the traditional route. R1 plus R2 is the traditional plus the new route. So that's what we're going to get. And for amplification, like Maha had asked, what is the wavelength? You see that in each case, something of order 1 is selected as the best spacing. So the amplification is much more for this particular thing, and that's what is going to be visible as streaks. That spacing will be visible. And the interesting thing you see here is that the red is the less viscous, blue is the more viscous, and you see that blue, the more viscous side of the channel, is very energetic in streaks if it's a channel, but if it's Couette flow, it's the other way around. So you see entirely the opposite thing. And you also see, and this, so like this would be the unstratified one. This dashed line would be the unstratified. So on one side, it becomes more energetic. On another side, it becomes less energetic. In Couette, on one side, it is the same, and in one side, it becomes more energetic. So all these interesting differences happen. When you have R1 and R2, the new route, when you include that, this went from 0, 1 and 2 to 10. So this has become very, very big. Whereas in the Couette, nothing much has changed. R2 does very little. Here, R2 is the winner. And so it's actually like made very energetic streaks on one side of the channel. Note, it's breaking symmetry. This thing is breaking symmetry. So the streak generation is enhanced very much in Poiseuille, not much in Couette. Hot and cold walls behave opposite to each other. And the reason for this is very, very easy to understand. Basically, like when you have forcing modes, you can force in many modes in Z, right? So the first one you'll do is this mode, and the second one you'll do is this mode. So basically an n equal to 0 and an n equal to 1 mode. And these have respectively the highest possible amplification and the next highest. What happens is in Poiseuille flow, if you didn't have viscosity variation, U prime, the shear, is perfectly antisymmetric. Because it's perfectly antisymmetric, it works, it cancels out the first mode. So only the second mode can operate. So it's a weak mode. So that mode is not going to produce too much of streak generation if it was unstratified. In Couette, it does great. The first mode itself is very much like this because the U prime is practically symmetric. Now, when you have viscosity variation, you bring a lot of asymmetry, break-in symmetry into this problem. And beautifully, like now the Poiseuille flow can respond to the first mode, which it could not respond to earlier. So because it's responding to the first mode, you're kicking it through this U bar. You're now going to get like much bigger, and you see this kind of alternating behavior. So we repeated all this for a turbulent mean flow, and we compared it to direct numerical simulations. And actually, like, you know, the streaks that you see in DNS have something to do from this linear analysis. This okay? Okay, so now we're going to do a completely different approach to this problem. So in the previous one, we showed why like different shear flows are going to be different, and like Maha said, different scales are also going to change the answer in a dramatic way. So this is just a hint of what all can happen. So the growth of perturbation energy. Now, what happens is take the Navier-Stokes nonlinear and make an energy equation out of it. So take Navier-Stokes, dot it with velocity vector, integrate over space. You'll get an energy equation. And that energy equation looks like this. It's the famous Reynolds or equation for energy growth for the full nonlinear. So you have d energy by dt is production minus dissipation. This is actually a positive term and this is a negative term. Production minus dissipation. You'll see that the initial amplitude of your perturbation doesn't matter. So even if you had a small amplitude or a big amplitude, the energy growth will just be proportionate to what you gave. So therefore, it's actually a linear behavior. You got a nonlinear Navier-Stokes at a very high Reynolds number, and its energy growth is linear. This is the important thing. And this has been an important thing in the mindset of all people. And so there is a dogma which says everything is linear in the beginning. And so linear is put on this big pedestal, even though the Reynolds is very, very big. And so you'll see also that from all simulations, you'll see things like this. Initially, everything is linear, 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 and then like nonlinearity takes over once the mean flow is changed. Otherwise, like in the full high Reynolds number flow, everything is linear. What we derived is the Reynolds or equation for viscosity stratified flow, and that thing is no longer true. That independence from amplitude is no longer true. So we expect that nonlinearity is going to come in at 0 time and in a very fundamental way. So that's what was our hypothesis, and we did this standard technique called direct adjoint looping, for which we had to derive the adjoint Navier-Stokes for this case. So we derive the adjoint Navier-Stokes, we do this direct adjoint looping. So we basically do direct numerical simulations, march from time equal to 0 to t, march from t to 0 in the adjoint equation, and keep doing this looping, and you'll converge to any optimal perturbation. This is a standard technique. It's actually a glorified, power iteration. It's glorified power iteration that we are doing. So here we are asking a slightly different question. We are saying we are going to put like a perturbation of this size away from the laminar. And so like where on this infinite dimensional sphere should we begin such that at time t, we are at the biggest energy possible. So what is our initial perturbation which will give me the most energetic final state, which may or may not be what the turbulent state is. But this is the optimal perturbation seen, and this is the question we ask. Now, if we use the linear optimal, like everybody uses the linear optimal because that's the dogma in the field, you would get like the perturbation as a function of time, the optimal perturbation as a function of time like this. In fact, these things are span-wise aligned. They're not even stream-wise aligned. You're getting completely the wrong answer if you did linear. So this is telling us that, and only with the non-linear, we get this streak generation, namely the lift-up mechanism. So this is telling us that it's non-linear from the word go. And this is what it looks like with time. So in this case, we didn't put streaks. We just put this ball and we asked which is the optimal perturbation, right? So streaks are coming out automatically whether or not it's viscosity stratified. So we're getting these streaks at low time and later time. And you see that there's lots of differences compared to the other one. First of all, like these things, like this part is thinner and this part is fatter. It's not like a sinusoidal perturbation. The whole wavelength is like bigger here and smaller here. And so like this is what it is like at short time, where, you know, near the wall, you get very sharp streaks. In the center, you get diffuse streaks. And this is what it is at short time. At long time, everything is dead on the hot wall. You basically got turbulence without streaks in the hot wall. So what on earth is happening? We should always get streaks, right? But these are gone at the hot wall. And whereas at the cold wall, they're persisting. So cold wall, they're even strengthening, but in the hot wall, they're dying away. So this is the level of, very nature of turbulence has changed upstairs and downstairs. And the mechanism for this is very simple. We talked about low speed and high speed streaks, right? Now, these are also viscosity streaks. Because on the hot wall, you took like low viscosity fluid and you pulled it up. So the high speed streak is of low viscosity. Low speed streak is of high viscosity. On the cold wall, it's exactly the opposite. So like what happens is you have these two, a high speed, fast flowing fluid next to a slow flowing fluid, fast flowing fluid next to a slow flowing fluid. But now on the cold side, the low viscosity fluid is faster, high viscosity fluid is slower. So like when the low viscosity fluid is faster and high is slower, it's easy for it to stay that way. Like this will basically behave like a wall and that thing will keep racing through. So like it's going to be maintained for a very long time. So streak lifetimes can be very, very long. Now on the hot side, you'll see that the faster guy is high viscosity, slower guy is low viscosity. And because of that, I'm nearly done. Because of that, this thing is going to drag the low viscosity fluid and all the streaks are going to get killed. So this is the fundamental mechanism that we worked out. And this is my summary, most of which you saw. Streaks are everywhere, viscosity variation is everywhere, and we've started looking at them together. It's just a first step. There's lots to do. There's a new mechanism, entirely new mechanism for streak generation. Even if the old mechanism was not there, this one would generate streaks. And it competes or cooperates with the old depending on the symmetries of the shear, sign of the shear and so on. And in a heated channel, we saw that everything is nonlinear from the word go, and the symmetry breaking is prominent. So we believe that turbulence is going to be different in these flows. Thanks for your attention.
Thank you so much, Rama. We can take a few questions.
Can I ask a question about how this mechanism that you suggested in the nonlinear regime can give rise to the equivalent of puffs and slugs and so on, which you have in viscosity unstratified? So just uniform viscosity flows when you think about transition to turbulence through these localized structures which gradually grow first in the transverse direction and or in the longitudinal direction. Are you suggesting something similar is happening in the viscosity stratified
structures in which these little spots, turbulent spots, grow? So like this is what is the standard, like in a pipe flow, and it could be spots in a boundary layer or slugs in a pipe, whatever. So they grow into this sea of streaks. So you need the sea of streaks for them to grow, and that's what happens. Now, in what we are saying is that's going to fundamentally change, but somebody has to check out this hypothesis. That's going to fundamentally change, partly because all these streaks are low viscosity, high viscosity. So there's viscosity, bumps all along, which is like leading you to inflection points, which lends the streaks themselves to instabilities. So the streaks themselves may not survive. And certainly on the hot wall, we saw how they all died off. So if they're all dead, like that's already like a turbulence that you're getting there without big structures. You're getting a completely different turbulence, which may or may not result in turbulent spots. These spots and slugs are a very, very special secondary instability sitting on these streaks. And now on one side where these are retained, it's going to be modified because of all the inflection points you put in. On the other side, it may just not happen. So all of these are going to get dramatically changed.
If you decrease the viscosity gradient, so like the streaks that die down, just the time. Yeah, the streaks that die down, if you decrease the viscosity gradient, do they still die down at a different time? Like no matter how small the gradient is, do they all eventually die down on one wall?
Yeah. Basically, it's a question of time scale. Like the smallest viscosity variation is enough to break symmetry, to do things. That's why this is so dramatic.
In an ensemble sense, is there a steady state of what would be the streak distribution? These streaks are sort of temporal, right? They arise. So in an ensemble sense, is it possible to write like a averaged view of streak distribution?
People are looking at things like that because like in the ocean and wherever there's streaky structures, they're interested in mixing and all. So they want to see something like an average energetic component of these streaks. So yeah, it is possible. Like you can do a direct numerical simulation and actually average it out, and it'll be like a very reliable and repeatable number.
Okay, so let us thank Rama again for this nice talk.